Valve and camshaft placement configuration. Two basic valve and camshaft placement configurations of the four-stroke gasoline engines are used in automobiles. Overhead valve. As the name implies, the intake and exhaust valves on an overhead valve engine are mounted in the cylinder head and are operated by a camshaft located in the cylinder block. This arrangement requires the use of valve lifters, pushrods, and rocker arms to transfer camshaft rotation to valve movement. The intake and exhaust manifolds are attached to the cylinder head. Overhead cam. An overhead cam engine also has the intake and exhaust valves located in the cylinder head. But as the name implies, the cam is located in the cylinder head. In an overhead cam engine, the valves are operated directly by the camshaft, or through cam followers, or tappets. Some engines have separate camshafts for the intake and the exhaust valves. These are called dual overhead camshaft engines. Valve arrangement. L-head engine design. Engines that use the L-head engine design also are called flathead or side valve engines. This was once a popular valve arrangement. This engine type is characterized by having no moving parts contained in the cylinder head. The head serves only as the combustion chamber. The valves are located in the cylinder block, beside each cylinder. The intake and exhaust manifolds mount to the cylinder block. The valves were opened and closed directly by the camshaft. A major drawback of this design was that the air-fuel mixture had to change direction to reach the combustion chamber. This limited the overall performance of the engine. I-head engine design. I-head means the valves are directly above the piston, which are also called overhead valves. The valves are located in the cylinder head. The design allows air and fuel to move easily into and out of the cylinder with little restriction. Variations of this design are used in today's engines. T-head engine design. In the T-head design, the valves are located within the block, one on each side of the cylinder. The difference between this design and the L-head design is that two camshafts are needed. Because of this extra expense, T-head designs have not been used in the automotive industry for many years. F-head engine design. The F-head engine design is a combination of the I-head and the L-head designs. The intake valves are located in the head, and the exhaust valves are in the block. It has some of the advantages of the L-head and I-head designs. However, the increased cost of parts is a disadvantage. Valve and camshaft operation. In overhead valve engines with the camshaft in the block, the valves are operated by valve lifters and pushrods that are actuated by the camshaft. On overhead cam engines, the cam lobes operate the valves directly, and there is no need for pushrods or lifters. Lifters may be used between the camshaft and valves. Cam lobes are oval-shaped. The placement of the lobe on a shaft determines how far the valve will open. Design of the lobe determines how far the valve will open and how long it will remain open in relation to piston movement. The camshaft is driven by the crankshaft through gears or sprockets and a cog belt or timing chain. The camshaft turns at half the crankshaft speed and rotates one complete turn during each completed four-stroke cycle. Engine location. The engine is typically placed in one of three locations. In the vast majority of vehicles, it is located at the front of the vehicle, in front of the passenger compartment. Front-mounted engines can be positioned either longitudinally or transversely with respect to the vehicle. The second engine location is a mid-mount position between the passenger compartment and rear suspension. Mid-mount engines are normally transversely mounted. The third and least common, engine location is the rear of the vehicle. The engines are typically opposed type engines. Each of these engine locations offers advantages and disadvantages. Front engine longitudinal. In this type of vehicle, the engine, transmission, front suspension, and steering equipment are installed in the front of the body, and the differential and rear suspension are installed in the rear of the body. Most front-engine longitudinal vehicles are rear-wheel drive. Some front-wheel drive cars with a transaxle have this configuration, and most four-wheel drive vehicles are equipped with a transfer case and have the engine mounted longitudinally in the front of the vehicle. Total vehicle weight can be evenly distributed between the front and rear wheels with this configuration. This lightens the steering force and equalizes the braking load. With this design, it is possible to independently remove and install the engine, propeller shaft, differential, and suspension. Longitudinally mounted engines require large engine compartments. The need for a rear drive propeller shaft and differential also cuts down on passenger compartment space. Front engine transverse. Front engines that are mounted transversely sit sideways in the engine compartment. They are used with transaxles that combine transmission and differential gearing into a single compact housing fastened directly to the engine. Transversely mounted engines reduce the size of the engine compartment and overall vehicle weight. Transversely mounted front engines allow for downsized, lighter vehicles with increased interior space. However, most of the vehicle weight is toward the front of the vehicle. This provides for increased traction by the drive wheels. The weight also places a greater load on the front suspension and brakes. Mid-engine transverse. In this design, the engine and drivetrain are positioned between the passenger compartment and rear axle. Mid-engine location is used in smaller, rear-wheel drive, high-performance sports cars for several reasons. The central location of heavy components results in a center of gravity very near the center of the vehicle. This vastly improves steering and handling. Since the engine is not under the hood can be sloped downward, improving aerodynamics and increasing the driver's field of vision. However, engine access and cooling efficiency are reduced. A barrier is also needed to reduce the transfer of noise, heat, and vibration to the passenger compartment.